So perhaps you just finished reviewing the cross product, or maybe you didn't, but either way, I am now going to assume that you're very comfortable with the cross product. And so now I'm going to do an example, a couple of examples actually, involving the magnetic force and on a point charge. Okay, so here's the Lorentz force, and I remind you, the idea here is that we have a moving test charge, that's capital Q, and it can be affected, will be affected, not only by a magnetic force created by any magnetic fields that happen to be around, but also, of course, by any electric fields that happen to be around as well. And so that's what this is. So Q times E is simply, of course, Coulomb's law, and so that's the electric force that we know so well by now. And then Q times V cross B is the magnetic force. So the total force is the electric force plus the magnetic force, and that sum is given the name, as I say, the Lorentz force. So here's an example. And this example is not as artificial as it seems, as it turns out. And I'm going to take this example, I'll solve it, and then I'm going to twist it to another purpose. Anyway, so we have a proton fired into a uniform magnetic field at very high speed, very high energy. Specifically, we'll shoot it into this uniform magnetic field that points straight upward. Now, I don't know where the magnetic field comes from. It came from some source currents that they're not in the problem. They're not important. All we need to know is the magnitude and direction of the field that they have created. But the magnetic field value is given to you here, and I'll talk about that in just a moment. But whatever the source of the magnetic field is, some currents that we neither see nor control. Okay? But whatever, the field is, by assumption, uniform in space. It points everywhere vertically, and it has a constant magnitude. All right. So we fire this proton into the field. The proton is moving at a nice, respectable, a little over 32 million meters per second, 3.2 times 10 to the 7th meters per second. To the right, the magnetic field is pointing straight upward. And the magnetic field has a magnitude of 1.2 times 10 to the minus 3 Tesla. Tesla, I haven't talked about. We'll talk about more detail, what it is, where it comes from. But for now, the only thing you need to care about is that Tesla, abbreviated capital T, is the SI unit of magnetic field. All right. With all that information, then calculate the force that the proton experiences. All right. So step one, we'll draw a diagram. All right. And so let's see. We have a uniform magnetic field that's pointing straight upward. So I'll draw it like this. Now, I will tell you, it is going to be a rather peculiar, not terribly difficult, but a rather peculiar arrangement of currents that can produce a magnetic field that's constant in this way. But it can be done. Then we have our charge. Call it Q sub P, I guess. I could just call it E positive or something, but whatever. And we'll fire it into the field. Its initial velocity, anyway, is that. Okay, so B is this way, V is that way. Right. And the numbers are given. Q, B, B, that's all we need. Okay. Next, we'll need a coordinate system. Now, back in the dim and misty, back in the past, when we were dealing with electric forces and then electric fields, we spent a lot of time talking about different coordinate systems: Cartesian, spherical, cylindrical. And we became reasonably comfortable, maybe not experts, but reasonably comfortable with working in them. And I haven't forgotten those, and those are going to come to us in magnetic fields, and we're going to have to deal with them in magnetic fields. We will find that most of the time, the coordinate system that will be of most use to us is going to be cylindrical coordinate systems. Okay. In this particular case, though, because I have this nice artificial textbook problem where my magnetic field is nice and uniform in space, it's just as easy, frankly easier, to choose a Cartesian coordinate system. And so I'll choose a Cartesian coordinate system, and I don't know if you guys can see this on the recording, but whatever, I will choose upward to be the Z direction. I will choose to the right to be the Y direction. Out of the board, perpendicular to the board, is going to be the X direction. And ordinarily, I wouldn't even bother putting the X direction in here, but because of the right-hand rule stuff, probably I should. Okay, so that's our coordinate system. All right, so that's our coordinate. Okay, so now we're going to solve the problem. All right, we have a charge, we have a magnetic field, we know that that charge is moving with some velocity, so all of that suggests, whoa, what was that? All of that suggests certainly a magnetic force. As soon as I hear magnetic force, I think about the Lorentz force expression, because there's Q, B, cross B, good, that's the magnetic force, and then we have to look around for any electric fields around that might create an electric force. Stare at the problem a few minutes, and you should be able to convince yourself there is no electric field here. So E is 0, and so the net force on the thing simply becomes Q V cross B. Okay. Doesn't really matter which one we do first. Let's get the direction of the force first, because that's just sort of analyzing the cross product. All right, cross product. So you remember how to do the cross product. V is your first vector, B is your second vector, and so the way that I like to do it, this is what I did in my review recording, to determine the direction of the resultant vector, the vector that results from crossing V into B, right-hand rule, with the palm of my right hand, or palm of your right hand, push the first vector listed, that's V, into the second vector listed, that's the magnetic field vector, through the angle theta between them. Well, the angle between V and B, when they're placed tail to tail, is just that, 90 degrees, right? And so you push V into B, and then the thumb of your right hand automatically points in the direction of the resultant vector, which in this case is the magnetic force. And so the answer to the direction of the magnetic force is out of the board. And so I will draw that like this, I guess. So the force on it here points out of the board, and I'll label it like so. You'll notice how important it is to clearly label your various vectors. How easy it is to get confused. This is a big reason why I use different colors. And you know, when you take tests, my tests, other tests in future classes, really, you know, colors help a lot. Okay, so go invest in a set of colored pencils, and thank me later. Okay, so the magnetic force direction is this way. Now we need the magnitude. And that, of course, is pretty trivial. The magnitude of F is simply the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. In this case, the angle between them is pi over 2, and sine of pi over 2 is 1, and so we end up with F is equal to just V times, I'm sorry, Q. Sorry, there's a Q here. Q times V times B, and so that's 1.602 times 10 to the minus 19th coulombs. The velocity 3.2 times 10 to the 7th meters per second. The magnetic field 1.2 times 10 to the negative 3 Tesla. Crank out those numbers, and I got 6.1 times 10 to the negative 15th newtons. Couple of things. How did I know it was newtons? Think about that for a moment. Pause the recording. Think about it. How did I know it was newtons? Okay, you're back. Good. And the answer is, because I'm calculating a force, it's got to be newtons. All right. So this then would enable you to figure out how a Tesla is defined. So you can think about what does Tesla have to be in order for the right-hand side of this to end up with units of newtons. So you can work that out. Anyway, so the final answer to the problem is the magnetic force on the proton has a magnitude of this pointing that way. Okay, that's a good stopping point for this recording. The next recording, I'm going to take the same example and turn it on its side.